Hello, everybody, and welcome to another episode of the Vidor Locksmith Show. My name is David Gibson. I am your host, and today we are unlocking the secrets to success in the oil and gas industry, one interview at a time. I am super excited about this episode, mainly because I've got my dear friend Dan Cervantes being able to come on the show, a guy that I actually interviewed, to be able to bring him on at Lodestar while I was still there. So I'm really excited about today's show. I'm really excited that you guys are tuning in and watching today. I know that we should have a ton of people joining us. We've already got a lot of comments rolling in. We've got tons of people watching. So we've got, let's see, I want to be able to try to see if I can do this right this time. We've got Donald watching from Nigeria, Mohammed watching from Kuwait. We've got Tejas from Houston, Texas, Abu Dhabi checking in, Longview, Texas, Santiago in Perth, Scotland. Look at this. Mr. Gupta from India. Guys, thank you guys so much for tuning in. Eric, who's watching on YouTube, he's a big fan of the show. He's always tuning in. Elisa from Brazil. This is going good. We've already got a lot rolling in. So, guys, as per normal, I gotta put this one out there. Costa Rica. Sorry, I almost clicked on it. Mr. Nathan LaRue, buddy of mine from Oklahoma City. Thank you guys for tuning in. We even got Malaysia. Oh my gosh, I could just there's so many different places that are tuning in for this. I'm really excited about it. Okay. Wow, the comments are coming in really fast. So guys, let me know where you're watching from. Let me know what company you're working for as well. I've got no problem giving a little bit of a shout out to anybody's company and where they might be working at. Or, hey, if you're even looking for a job, let us know. Put it on there. Say, I'm watching from here, and I'm looking for a job. So, Mohammed from Oman. Oman is a beautiful place. If you guys have never been there, actually, Eric and I from Lodestar International actually went there a couple of years ago. It's a beautiful place. So, if you guys haven't been, be sure to check it out. There we go. Brad LD, Stable Drill of Midland, Texas. That's what I'm talking about. Lee House. Big fan of Lee, Lafayette, Louisiana, in Pennsylvania. So appreciate that, sir. Wow, the comments are rolling in so quick. It's hard to keep up with them, guys. We've also got Mauricio from Colombia. Guys, thank you guys so much. I do appreciate it. You guys all tuning in. So I've got a couple of actual updates. For once, I have something to be able to say on my show. So we just started the email program. So if you go to the website, gibsonreports.com/Vidor Locksmith, there's you type in your email, your name, last name, hit enter. It'll send you an email that says, hey, did you sign up for this? You say yes. Then you guys will be on the email list. I actually sent out the first email last night. What we'll probably do is send them out on Mondays and maybe Thursdays, the night before the show. Monday to be able to recap the show that was on Friday. And then Thursday to be able to just remind you that, hey, we have a show coming up the next day. So if you guys want to, be sure to go over there and do that. Also, you guys, I have to do this real quick. My buddy Aaron Baxter. Aaron Chili Baxter from Granbury, Texas. Thanks for tuning in, bud. Guys, please tag a friend. Let somebody know that we're about to have some great content on here for you guys. Let us know where you're watching from. Tag a friend. Share the show, hit the subscribe, but all those things. I know we've got 54 people tuning in on YouTube. It looks like we've got about 90 or so over on LinkedIn. I have a feeling we're probably going to get up over 200 today. I think that number is going to keep climbing as we let people keep getting people notified that the show's going on. So trying to think, what was the other notification or other email? We've got the new set. Actually, if you guys didn't notice this, I actually went ahead and tore down the old Vidor Locksmith set and put up a completely new one here in the office. We're not doing very many in-person interviews, so I didn't need to really have a set for in-person interviews. So we're going to redo all of this. We just finished this on Wednesday and getting everything set up and ready to go. That's about it. So as per normal, if you guys haven't seen it, I'm going to run. So Duncan says morning all. And my buddy Drew, thanks for tuning in, man. I always do appreciate it. So what I'm going to do here is we're going to play our commercial, because if you guys haven't seen it yet, we've got the How It's Done. All the episodes are on YouTube. All the episodes have been broadcast here live on LinkedIn as well. And let me see here. Where is the button? There it is. So after I play the commercial, we'll be back with our guest for today. All right, and we're back with you guys. Dan, welcome to the show. Thank you so much, sir, for being here.
Hey, thanks for having me, David. I really appreciate me being on and you asking for me to come on. It's really an honor. I've seen your podcast grow when you started it. And it's kind of going to where we'd hope it would be when you started. So I'm really happy to see that.
So this is, like I told everybody earlier, this is a special moment for me because actually, Dan, I do consider to be a friend of mine. We've worked together in the past. And then now being able to get to have him here on my show, it's going to be awesome. We've got some amazing stuff. We actually went through this presentation the other day just to make sure we had everything worked out. And I'm telling you guys right now, you are going to be amazed at some of the stuff that you're going to get to see here today. So let me double check, make sure that we've got everything ready to roll here. I know usually during this time is like people are asking me like, I didn't get the link or I don't know how to join or whatever. So usually I have to, help out the stragglers as they're getting into the classroom, you guys. But looks like we've got everything here good to go. Thank you guys so much. All right. I think we'll let this one just roll then. All right, Dan, I will turn it over to you, sir, and let you be able to educate everybody on what you don't know about downhole drilling dynamics. Wait. There we go.
There we go.
All right. Thank you, sir. I'll let you rip.
Perfect. All right. Again, thanks for having me on, David. It's a tremendous honor to be on the podcast. A little intro to myself. My name is Dan Cervantes. I'm the operations lead at Lodestar International. I've been here for about 4 years now, so quite a bit. And today I really want to show you guys and give everyone in the industry kind of an insight as to what we see as a technology company in drilling dynamics, because it's been a pretty hot topic, but not everyone gets to see it. A select few, obviously we who work with the data, work with the tools, drilling engineers, subject matter experts, researchers, but I think it's very important for everyone in the industry to know what's out there and kind of what's happening downhole as well. So kind of just give a little overview of what we're going to talk about. Again, I'll go over kind of what the data means, what is drilling dynamics data, and the technology that people are using to gather this data. And then we'll do a deep dive into kind of just some examples of what we see and kind of interesting stuff that you otherwise wouldn't get to see. We'll talk about your MWD and what it does to your motor, torsional oscillations, and what stick slip actually looks like downhole. We'll get into true weight on bit. That's one of the hot topics that people always want to talk about: weight transfer. So we'll get into that. Turning to the left, negative rotations. I mean, that's again another hot topic that sometimes people don't know is happening, and then we'll kind of see, and then we'll talk about the forgotten dynamic that people always forget to talk about, but it's very prevalent. It's very, very useful. So let's go ahead and dive into the technology. So typically we have two different kinds of tools. We'll have at-bit tools, and one of the things being, the characteristics being, they're compact. You don't want to increase your bit to bend too much. You want to, and then you get true measurements at the bit where you're actually cutting rock and where it matters the most. So at Lodestar, our technology is the iSub. So it's a short sub, goes between the bit and the motor. It's less than 1.5 feet long, and obviously we get true correct measurements at the bit. The other type of tool you might see is collar-based tools. These are very versatile. You can place them usually wherever you want in the drill string and their BHA. It also gives you the ability to capture multiple measurement points. I mean, in this example here, we've had as many as 5 tools downhole, and our tool for this solution is the iString. So basically, it's iSub built to be put anywhere in the drill string. So kind of the sensors that you'll see on these tools, we'll see accelerometers to measure G-forces. Those are used to capture vibrations as well as rotation, sometimes inclination even. Some tools will have gyros. Typically those capture rotation. Strain gauges, they'll measure force. You'll get your bending, your torque, your weight on bit, very important. And then also pressure is one important measurement that we're capturing downhole in some cases. So for example, our tool is the I-string and the I-sub, which you guys see here. What we capture is lateral and axial, or lateral vibration in two directions. So we have X and Y, axial vibration. We have strain gauges that measure weight on bit, torque, bending in two directions. So we have X and Y bending. The magnetometer, we capture inclination as well, and temperature. So let's go ahead and look at what this data looks like and kind of give an explanation for some people who may not necessarily know what we typically see. So when we're talking about drilling dynamics, we really want to talk about high frequency data. And the way we measure the sampling frequency is in hertz. So it's 1 over second. So you'll hear this terminology done around. It's like we're measuring at 50 hertz, we're measuring at 100 hertz. Some companies will measure up to thousands of hertz. And what that means is they're measuring that many data points per second. So when I say, hey, my tool is recording at 50 hertz, we're measuring 50 data points per second. So you can imagine that over the length of the well or over the length of a section, that adds up to millions and millions of points when you gather up all the sensors that we're looking at. In comparison, what we typically see from an EDR is 1 hertz. So 1 data point per second, sometimes even 0.2 hertz, so once every 5 seconds. And there's a difference between the way companies record and sample data, and it's important to make the distinction between the two. So there's recording, which is what you're writing to memory, what you're storing, or what you're even streaming in some cases, and then there's sampling. So when you sample, that's what your tool is. That's what your tool is doing. You're gathering data at this frequency. When you record, that's what you're actually writing. So kind of the three different or three examples of that are continuous data. So you're measuring at 50 hertz continuously. You're writing it to memory continuously. That's a lot of data. Some companies will do burst, so you get a really high burst of data every 15 minutes, every certain amount of time, up to thousands of hertz. And then some companies will even do statistical data. So every few seconds, you'll gather the max, the min, and the mean. So here we have an example of, here we go. Here we have an example of what Lodestar is typically recording and giving to customers. So on the y-axis, we'll have weight on bit. This is one example of our measurements, the weight on bit. And we're plotting versus time because that way we get the most granularity in our data. This example in particular, so we're recording at 50 hertz. Again, so we have 50 data points per second. We are sampling and recording continuously. So that means that we are, every time we record a data point, we're writing it to memory. This gives us the ability to do frequency analysis, see very high oscillations downhole, and ultimately get the best picture of what's happening at the bit. So if we go to this next example, this is the same data set, but as an example, we say, hey, we're recording at 50 hertz, or we're measuring at 50 hertz. We're sampling continuously, but we're only recording the max, the min, and the mean every 1 second. So what this does is it gives you an idea of what's happening downhole. So you say, yes, I'm having weight on bit oscillations, and these are my max and min. But if we get this data, we're missing a lot of the picture. We're not really able to see, what's causing this, how rapid are these changes, and once we zoom into these kind of very minute details, that starts to matter, especially when you start getting into frequency analysis and determining what's causing your problems downhole. And kind of another example, which we typically don't do, but for some customers will ask for ease of plotting and just having the right equipment and software to handle it, is again, we're sampling at 50 hertz, but we're recording the average every 1 second. So obviously this is kind of the lowest resolution data you can get, and we're only seeing an average, so you're really missing all the details that's happening. So it's very important to both record and sample at high frequencies, so we're able to analyze everything at as best we can. And David, and anyone, if you have any questions, feel free to put them in the chat. I know a lot of this is very new, it's very different. So any questions popping up, David?
So we do have one question already. Let me see if I can go back and grab this one. So this is actually, because it's not showing his name, this is Alexis, who's a PhD student at King Abdullah University.
Right.
Do you have any FFT and then filtering, since a lot of the noise in the data?
Right. So we will do FFTs. We try not to filter the data. The reason being that obviously filtering data can help in some cases, but too much filtering will kind of reduce the granularity of the data. So we start to lose some resolution. So we try not to do it too much, but we definitely use FFTs, spectrograms to analyze vibrations, determine resonant frequencies, and see how they're affecting our drilling or BHAs.
So then we had another one. So Armin, who's always a fan of the show, asked, what is the memory size of the tool?
So our tools, for both our tools, the memory will depend on the recording frequency. So right now we have 3 recording frequencies. So we'll do 20 hertz, 50 hertz, and 100 hertz. So our max time that we can record at 20 hertz is 15 days. So that allows us to capture, almost an entire well. At 50 hertz, we'll get 6 days of recording, and at 100 hertz, we'll get 3 days of recording. So we'll tailor, we'll tailor that frequency to what the customer needs and how long we're expecting to be downhole.
Another one. So this is Mr. Michael Phillips. Michael, thank you for watching this show. Do you have the capability to convert from time-based to depth-based?
We do. And the way we do that is every time we process this data, we match it to EDR. So obviously EDR, the best we get usually is 1 second. So when we do that conversion, we can also match it with depth. Now, the problem with doing depth-based analysis on such high frequency data is that you'll lose a lot of granularity. So for every 1 foot or every 0.2 foot, we'll have 1 data point, where in reality, that 1 foot could have taken you 5 minutes to drill. So you're losing a lot of data when you do depth-based analysis, but we will do it. But as a representation mostly, and to look for trends. But when we're looking at, very high frequency data, using depth-based analysis isn't always the best.
Wow. I mean, the questions are coming. So we've gotten this one several times now. Recording is great, but we need to make decisions in real time, ? So there's been a couple of people that are asking about, is your measurements in real time? I have when I worked at Lodestar, I had my answer for this one, but I'll let Dan answer.
Right. So we are working on real-time tools, and we are planning for a release in the next month or so. So in the next month or so, Lodestar will be announcing a real-time tool, real-time telemetry. So you will see this data that's very important in real time. Now, obviously, there's other providers that have data in real time. We can go into the cost and things like that, but it's available. We're making it available, and we're making it really cost effective. So because we want everyone to have this data, what we see typically from real time tools and real time telemetry of downhole dynamics is that it was built for offshore. So when customers onshore try to bring this data on and try to learn more about dynamics, it's too expensive, and a lot of people are priced out automatically. So we're trying to make it affordable, very accessible for customers for the onshore market.
So we've got some other questions about the real-time stuff and getting into the technical specs of the tool. So I'll let you answer this one real quick. What are the collar sizes available? And then I've got one more right after that.
So right now we have a 6 3/4 inch OD tool with NC50 connections. So we can cut the connections to any kind of connection that fits that size, that OD. And then we also will be releasing soon in the next month as well, a 5-inch OD collar-based tool. So we'll be able to do drill hole sizes, 6 3/4, 6.5, things of that nature. So we do have different tool sizes ability. And, I want to encourage anyone who has specific questions about tool sizes, what we record, kind of more information, our tech specs, to visit us at lodestarint.com. And I'll once we're done with this presentation, I'll put a link to our page, and we'll have a lot more examples of what we can do with data on there.
Here, I'll get it queued up right now so that we can drop it into the comments if you guys want to. There we go, lodestarinternational.com. You guys be sure to go and check that out. So we got one more question here that I think is good here. And then I'm going to tell you guys, one, connect with Dan, send him a LinkedIn connection request. If you guys haven't connected with me, do the same. This is the time. I'm being 100% serious. The information you guys are about to see over the next like 15, 20, 30 minutes or whatever is absolutely going to blow your mind. Please, please, please tag a friend in the comments. Let them know that now is the time to get clued in, or share this. I think you can share it fairly easy down at the bottom or whatnot. I cannot stress enough how excited I am to see some of this stuff, because I'm going to be geeking out about it. If anybody here is actually watching this and enjoys seeing, you know, interesting downhole drilling dynamics data, now is the time to tune in. So last question here before we keep going.
Do you record? Is that the?
Do you record MSE?
So MSE is a calculated value, obviously. So we don't record MSE, but we will calculate MSE. So we will, because we have data at the bit or in the string, we can record MSE at multiple points and determine where the energy loss is occurring. So the answer is yes, we will calculate MSE with our data, and obviously that's the true MSE at the bit.
All right, so we're getting like the questions are coming in hot and heavy now. Like I said, guys, you know, tag a friend. We're gonna keep the presentation going. We'll try to, if any of the questions that we haven't gotten, feel free to be able to ask them again later on. And I'll turn it back over to you, Dan. I'm out of here.
Cool. So both me and David have a background. And now let's get into the actual interesting stuff. So obviously we were talking about tools and data. Let's get into some real world examples and get into what's happening downhole. Both me and David come from MWD. You'd say most of the MWD equipment out there is positive pulse. Obviously you create pulses by restricting flow. Those pulses go up the liquid column in the hole, and you receive them at surface, decode them to see what's going on at your MWD. So if you take a look at this plot on the right, you know, an MWD guy would tell you, oh yeah, well, that's my signal coming up. You have your 4 sync pulses, and then we start beaming up a survey. But you know, I'd like to ask in the chat, have you ever had a drilling engineer ask you, hey, what's my pulse width? You know, what's my flow restriction? What kind of poppet are you running? And I mean, as far as my MWD experience, I did not have a drilling engineer reach out to me. Now, the reason I asked this is because what this plot actually is our bit RPM over time. So what we're seeing here is that every time the MWD is pulsing, that flow restriction is also causing a decrease in RPM for the motor. Now, obviously, it's something that people know is happening, or in the back of your mind, you say, hey, you know, obviously it's happening, but you don't really get to visualize it often. And this is one of the great things about high frequency data at the bit. So obviously, it's when you think about it, you can say, you know, this is really causing a hindrance for my performance. So let's take a look at a couple of examples of what's happening here. Here we have 2 examples. On the left-hand side, we have we're drilling an 8.5-inch intermediate with a 7-inch motor, and on the right-hand side, we're drilling a 6.25-inch production section with a 5-inch motor. So what we see here for on the left-hand side is that our bit RPM is dropping from 283, about 283 average, to about 216 RPM. On the right-hand side, we see that we're dropping from about 120 to 110 RPM. So, you know, we're seeing for the 7-inch motor, there's a 24% decrease in RPM output to the bit, and an 8% decrease in the 5-inch motor. So that's pretty significant when you think about it in the grand scheme of things. You know, you're designing your BHA, you're picking a motor, you're picking a bit for a certain RPM when you're not really getting that to the bit. Now you could say, obviously, we can see here this is off bottom data. You know, the reason I chose off bottom data for this example is because that's when it's easiest to visualize these things, and there's not really much cutting going on. So you can say, well, this is off bottom data. This can't really be happening when we're rotating or when we're drilling. So I'll present this graph. So for those of you who are not familiar with this, I'll give you a little bit of an insight. This is typically a graph you'll see from your motor manufacturer. They'll give you your bit RPM versus your differential. And what we'll typically see here is the curve that'll tell us, that'll tell the engineers at this differential, I'm expecting to get this RPM. So obviously this is very important when you're planning out your BHAs, picking your motor, picking the right bit. Now, obviously what's strange about this is that we have two very distinct pockets of data. Now, based on the previous graphs, we can say, hey, this first one here, that's when your poppet is wide open. So that's when we're not setting any pulses. This second pocket down here is when we have actual restricted flow from the MWD. So that's, I mean, when you look at it visually here, we're actually able to see what kind of implications these pulses have on your motor performance. So typically you'll see a curve like this. Now this is an actual fit. I'm just trying to indicate here what you'd see on a motor sheet. So when I'm designing or when I'm picking a motor, I'm looking at this black line and I'm saying, this is the RPM I'm expecting to get for my differential pressure. When in reality, because of this pocket of data here, your average RPM actually drops and you'll be closer to here in the middle, kind of skewed downward, which in this example with these representative curves is a 16% decrease in motor RPM. Now, again, this is on bottom drilling data while sliding. So this is when it matters the most when you're cutting rock. So, obviously David had a hand in discovering this, and when we kind of started noticing this was very important, and we're showing it to customers, and and they say, well, yeah, obviously it's happening, but until you visually see it, you can't really grasp the effect that it's having. Now, I'm not saying this to bash Positive Pulse. I'm not saying run another telemetry system. Obviously, Positive Pulse is very reliable. It's being used in the industry everywhere, but it's also important to know that this is occurring. So it's a consideration that should be taken when you're choosing your motor, your bit, configuring your BHA. David, I don't know if you want to let me know if you want to stop for questions here. Should I keep going? I know that there's probably some things going on here.
So we've got tons of great questions coming in. So Armin, who's being very active today, said, so this phenomenon could initialize stick slip.
That's a good question.
Thoughts and feedback on that one.
Right. So I'll go back to the previous plots to show you guys. It definitely could, if we look at, I mean, I wouldn't say initialized stick slip. I wouldn't go that far because stick slip means there's a stick phase and a slip phase, but you're definitely causing torsional oscillations at your bit, and it's documented and it's happening. So yes, obviously speeding up and slowing down your bit at high speeds obviously gives you the possibility of chipping cutters, bit damage, things like that. So it can induce, or it actually is, torsional oscillations happening at the bit.
So this one's going back a little bit further, but are you able to convert acceleration into the amount of movement, i.e. movement and distance?
So we are able to do that. You take I believe it's double integrate the acceleration, and you are able to calculate movement. It's a little misleading because we can't, there's obviously always some error when you do these integrations. So we don't know what that error is. So we can't necessarily say that you're moving in this direction for this amount of time, or moving in the other direction for a certain amount of time. But we can show the tendency of a tool or your bit or your BHA to want to move in a certain direction. So short answer, yes. Long answer, yes, with an asterisk.
Another one says, from Nisar, can we say motor bearing distance is also have a cause of lower RPM?
Motor bearing distance. So this is something we haven't taken a look at. Well, I can't say for certain. And in these cases, we mainly focused on looking at pulses, looking for different phenomena. But it's definitely something that we'd be happy to look into given the opportunity.
All right. So Armin with another question: how's the correlation to surface torque? I think we're going to get into this one later, but if you want to tackle it now, or if this is a segue, I can't remember what the next slide is.
Right. So I'll answer it right now. We don't see much correlation in this with surface torque, obviously because we have a big disconnect between where we're measuring this data and where the surface torque is coming from, which is the motor, obviously. So not much correlation here. I would not expect to see any torque spikes. This isn't like a big stall or anything like that. So very little to no correlation with surface torque when we're seeing this.
All right. I'll let you keep going, sir.
Perfect. So now let's get into stick slip. And it's important to talk about stick slip and first define what it is. And I actually had a hard time finding a good definition of stick slip. And I did find this one here from an article in Offshore Engineering. So stick slip is a mode of drilling dysfunction characterized by a cycle of the bit coming to a stop, then accelerating the speeds greater than the mean BHA speed. So the only thing that I will say about this definition is that it singles out the bit. What we've seen is that we have stick slip in the BHA, we'll have stick slip in the drill string, and obviously, again, we'll have stick slip at the bit. So that's my only distinction here. But again, stick slip is a torsional oscillation event. So we can't call everything stick slip. So let's get into this textbook example of stick slip. What we see here is we have a stick phase, pretty common. And right here, we're actually measuring bit RPM, and we're doing this over time. So this is a 30-second interval. What we see here is we have a stick phase with 0 rotation for 2 seconds. So this is 2 seconds where your bit is standing absolutely still. Once that energy, once we have enough cutting force to break rock at the bit, we have a slip phase where we'll spin our bit up to 600 RPM plus. So if you guys want to visualize this, let's take a look at what this looks like from a visual standpoint. So what we're going to look at here is about a minute of data of this stick slip happening. This circle here is going to be indicative of the sub. And we're going to have this bar here on the right-hand side, kind of measuring what you're seeing from the bit and what you're seeing RPM-wise. So let's take a look at what this looks like. So we'll see that we stay stuck for a few seconds. Then once the energy is released, we're spinning up to 600, 500 RPM. And what you notice there is that you do have some oscillation. So the bit is trying, the motor's trying to push the bit to break rock, but we're not really seeing that force. And this is in real time. So if you can imagine your bit spinning this fast and being stopped for this fast, and imagine the kind of forces, the torque that we're seeing at the bit when this is happening. So it's obviously very, very chaotic and something you do want to stop from happening. So that is our textbook example of stick slip. So when we think of stick slip, we say, hey, this is exactly what's happening. You're sticking, you're slipping. But if we take a look at a real example of what this looks like, it's not as clean, it's not as chaotic. Obviously, the previous example, it did happen, it does occur, but it's not always that easy, it's not always that simple. So this is an example where we have torsional oscillations. So we have wide bands of RPM mixed with isolated events in stick slip. So this is kind of what we expect more to see when customers say, well, we have stick slip. Well, it's not always stick slip. It's torsional oscillations with stick slip events. So to kind of get an idea of what this looks like, let's take a look at this animation. And notice in this one how we go through different modes of rotation. We do have kind of slowing, and then we have sudden spikes. We'll get almost close to 0 in some cases with very short rotations, and then we go kind of get steady, go back down. So it's very complicated, and it's not always so clean and simple. It's not always what you see in a textbook. So it's important to, one, have high frequency data to visualize this, and two, take the time to analyze and to actually determine what's causing this stick slip. So as you can see here, we're staying at about 100 RPM. See a big spike, kind of get steady, drop down back to 100 RPM. So it's very, very varied, very, very, very interesting. But it's very different. It's not always clean. It's always specific. So now that we have that, we can say, when we can break this down and try to determine where are these oscillations coming from? Where is the stick slip coming from? What's causing this? So let's kind of break it down for a little bit. If we take a look at RPM, what we expect to happen is that our total bit RPM is the sum of our motor output. So our motor rev per gallon times the flow rate plus the rotation put in by the top drive. So if I'm an engineer, I'm expecting this to be my RPM downhole. Now, when we plot what this actually looks like downhole, it looks a little something like this. So obviously it's very different. It's not what you expect, but we were able to analyze, see what's causing this torsional oscillation. And what we notice here is that the bits, because we're looking at bit RPM here, the bit is always turning at least the speed of the motor output. Now, what does that mean? That means your motor is performing the way it's supposed to perform. Every single time, the whole time I'm flowing on the motor, the bit is turning at the speed I'm expecting it to. Then why are we getting these oscillations? It looks obviously it's very periodic, it's very jerky. Then that means that the only way we can get these kind of oscillations where we're turning at least the motor speed is from the top drive. So every time we're inputting rotation from the top drive, it's not necessarily getting to our bit smoothly as we expect. We're getting stick slip, we're getting torsional oscillations in the BHA that are causing our motor to turn at a very periodic speed, and it's not constant. So when we have this, we can say that these torsional oscillations are BHA or drill string induced. Now, if we take a look, if we go back to our complex example that we looked at before, we do see periods of that. So we can say here, we're drilling pretty constantly. It looks like this is a torsional oscillation caused by the BHA or drill string. But the first thing we notice is, one, our motor line is dropped down. So this is our average motor output at the time. Obviously, this is caused by degradation of the motor. We're obviously, after some time, you do wear down your rubber. It's expected and it's known. So first, let's acknowledge that. Then what we can say is these kind of rotations, or rotations that are kind of in this area, these oscillations are caused by the BHA or the drill string. Because like on our previous example, we saw that if our bit is turning at least the speed of the motor output, then it's doing fine, and these oscillations are caused by the BHA or drill string. Now, then how do we answer these stick phases, or these oscillations that go below the motor output? These are caused now by the bit in the motor. The bit or the motor, I should say. This means that your bit or your motor are not performing the way they are supposed to perform. That's the only way you can stop rotation of the bit. It has to be obviously a bit interaction or an issue with the motor, seeing stalls, things of that nature. Now, once we start getting these oscillations like this, we'll start also seeing these higher spikes where we're spinning up to 350, almost 400 RPM pretty easily. So you can imagine that this is not being very nice to your bit. So I know there's a lot to unpack there, David. Feel free. I know there's probably a ton of questions on this. If you see any interesting ones, feel free to shoot them my way. We can go over them.
So actually, I think you were answering the questions as they were coming in. So Knights of Tigris, can you identify stick slip caused by the bit and one caused by the stabilizer? Can the tool differentiate?
Right.
That's
right. So
kind
the
of
answer,
already went over that one.
yeah, we went over that, and obviously it's like the data differentiates that, and that's why, again, for example, if we were looking at this at 1 hertz, we would see data points scattered like this. We would see very sporadic points. You wouldn't get this. We wouldn't see this granularity and be able to see. So the answer is yes. Yeah, we with this data, with our tools, we can determine when we're at the bit specifically, or we have multiple tools in the string, we can determine what's causing the stick slip.
So I think most people are just kind of listening. That was the only one that we'd like legit question, but you kind of answered it right there as we were going along. So I'll let you continue on, sir.
Great. So again, it's important to differentiate here between torsional oscillations, which are kind of these torsional oscillations, and actual stick slip, where you have zero rotation. And that's kind of a sticking point in the industry. So it's always important to say, we have torsional oscillations with stick slip events, or there is periods of stick slip with torsional oscillation. So next I want to talk about weight on bit. Weight on bit is one of the most important parameters in drilling. Obviously, that's how we drill, by applying weight to the bit. Now, with our sensors, with our tools, we're really able to get insight as to what's happening at the bit and what way we're actually transferring. So what I have plotted here is our weight on bit. Here we go. Our weight here on the y-axis, and we're looking at time again because that gives us the best granularity for high frequency data. So in the black, we have our surface data, so data from the EDR measured from hook load. And then in the orange, we have our ISO data at the bit. So obviously we can tell that they're lining up really well. We have some oscillations. That's kind of a side effect of high frequency data, but that's actually happening. So this is our perfect world example. What does that mean? In a perfect world, for your weight, your surface sensors have been calibrated properly. Your weight has been zeroed correctly before you drill the stand, and you have very little friction along the drill string and the BHA. So again, this is a perfect world example, and if someone tells you that this is how they're drilling, I'm inclined to not believe that 100%. But if we take a look at what's happening in reality, so this plot's a little different. What we're looking at here is we're looking at our surface weight on bit in the orange, and our downhole weight on bit in the blue. And this pink area kind of illustrates the kind of weight loss or friction losses that we're seeing from surface to our tool. So as you can see, as we increase with depth and time, we start seeing more differences. So what's happening in reality, the last calibration for your weight sensor at surface, it's probably unknown. I mean, if someone works for a drilling contractor in the comments, feel free to chime in on this. But we most of the time, we don't know the last time that sensor was calibrated. Again, in reality, your weight's zeroed correctly about 14% of the time. So we got this number from a Payson study of about 14 onshore wells, and they indicated that 86% of the time there was a incorrect weight on bit zero or no zero at all. So obviously that's one of the things that's very important, because you're relying on that measurement, on that process to determine what weight you're putting at the bit. And then obviously we know that friction is occurring and it increases with depth. That's the case with no matter what hole size you're drilling, no matter what section you're drilling as well. So these are the key things to focus on when we're looking at weight. And it's important that we acknowledge these when we're looking at this data. Now, as far as what it looks like when we don't zero properly at surface. So let's take a look at this example here. And there's a lot going on, so I'll go ahead and walk you guys through it. So again, we're looking at weight on bit on the left-hand side, and we're plotting our sub weight on bit in blue, and the black is going to be our surface weight on bit. And on the right-hand side, we're looking at the block height. So this indicates, are we off bottom? Are we not off bottom? What do we see here? What we don't see is a zero from surface when they are off bottom. What does this cause to our data? It causes an offset. So this is pretty common. Anytime we talk to customers, this is the first issue we try to address. because more than likely we're going to find some issue here. And we see that they start moving the block without any zero. There's some event that happens here, but it's still not correcting anything. So this is something that's kind of a important point to address in the industry, especially when we're talking, and a lot of people like to discuss, well, it's like, well, we'd like to optimize using surface parameters. It's like, well, the first thing is you have to know, are your surface parameters correct? The second thing is, are your surface parameters getting downhole? Are you getting that to the bit where it matters the most? So this is a very common occurrence. It happens all the time. So obviously this is a real world example. Let's get into kind of an interesting example, something we saw in an actual use case. What we have here is we have two I-subs downhole. We have an I-sub at the bit, and we have an I-sub about 77 foot back from the bit. We're behind the motor, we're behind a roller reamer, and we are behind an MWD. So about 77 feet of space between the two I-subs. And we're drilling a vertical 12¼ inch intermediate. So what we see here is that during these intervals, we're sliding. Now, you'd say here, even if we just had one tool in the BHA, you would expect that you're getting perfect weight transfer all the time, 100% of the time. Everything's getting to the bit. That's fine. It's minimal. It's stable losses. In reality, what we're seeing is that once we start sliding, we start seeing very large divergences between the top of the BHA and the end of the BHA at the bit. So this obviously indicates that we're having something getting stuck, where we're getting hung up somewhere. And this is very, very important, because when you acknowledge that you will have weight transfer issues, you usually expect them to be constant. You expect them to be stable. I'm not going to get this kind of divergence. So once we start seeing this, we realize that there's either buckling, there's a component downhole that is causing this to occur. So all in all, we're getting up to 30,000 pounds weight on bit difference in 77 feet of BHA in a vertical section with very little deviation. So this is super important, because think about what's happening once you actually get to lateral and you kind of get hung up like this. So very important thing to acknowledge. This isn't rare, and it's something that we like to address. Another thing that you'll notice operationally is that kind of here we have a kind of a straight line that indicates kind of a change in operation. So they might have picked up, zeroed again, and went back to drilling. Now what happens now? They zeroed incorrectly, more than likely. Now we're measuring more weight downhole than they're measuring at surface. So it's kind of these key things. So it's like, are you seeing what's happening downhole, and are you addressing issues at surface? So this is a hot topic. David, any questions there you think would kind of add to the conversation?
Other than we've had a couple of people. Sorry guys, I know a couple of people are watching. You're saying that you're seeing a blurred screen. Like I mentioned in the comments, we will post the PowerPoint presentation on Monday so that you can see these a little bit more clearly. It's possibly my internet. I'm broadcasting from out in the boonies, so just
same here.
Be clear. So I know that we had somebody that asked if it was slick versus stabilized to BHA. I can't find the comment. There it is. Jackie Cheese said slick versus stabilized motor, and I believe he was talking about some of the weight transfer.
Right. So this example in particular, so we have a stabilized motor, and there's also a roller reamer in the hole. So those kind of become the culprits of this. But it kind of highlights that it's important to consider that there are ramifications for running these. Hey, it's Brooklyn, or
yeah.
There's ramifications for running these tools downhole, and it's always important to realize that what you're expecting isn't always happening, especially from surface. So that's one of the key takeaways that I want people to take from this, is that we're expecting great weight transfer at surface. We're not that far in the hole. We're drilling a vertical section, but there's so many dynamics that can happen downhole that you would not even think of.
All right, so we've seen this question come up several times. I know where this is going to fit, but I'll go ahead and let you just give some foreshadowing. Question out of curiosity: have you ever measured events of backwards rotation at the bit?
Thank you for the setup. That is exactly what we're going to talk about next.
All right, Brooklyn, do you want to say hi to everybody?
Hi.
So the kids are at the office with me today, and they're just kind of hanging out. So Brooklyn wanted to be on camera. So everybody say hi and how cute she is. Hopefully we'll get a whole bunch of little likes and hearts and comments and stuff. Come on. You guys got to love Brooklyn. All right. So, Dan, I'll let you keep going. Or I should have this one. Okay. So Travis asked a question real quick. So Travis, he's actually with, I believe, with Total Directional. Any graphical representation of correlating differential pressure? We did have one on there earlier, but I'll still let you go ahead and answer that one.
Yeah, for this in particular, we definitely could graph this against differential pressure and see what the issues are there. And I would expect to see kind of a change in differential pressure there. But again, we are sliding, so that's almost expected. So it really depends on. So yes, we can do it. It just depends on are you guys drilling on differential? Is that what you're using as kind of a weight indicator versus just your weight on bit? So we can definitely connect after this, and we can talk about kind of if we see any correlations there with diff.
Well, thank you guys all for the Brooklyn comments, but there's 2 N's in Brooklyn's name, so just let y'all know. Ali had a good question. When using less stabilizers in the BHA, does it reduce the intensity of vibrations?
So it really depends on the application. We can't say yes or no. There isn't a defined answer for that. Stabilizers will sometimes cause certain vibrations and excitations in the BHA if you hit these nodal kind of RPMs. So the answer is yes and no. I mean, it really is. It's very specific to answer in such a general form.
Sorry, Dan. I know I'm being distracting. with
Hello.
Sweet. We also had a question earlier that had asked about the I can't find it. I was trying to earlier, but the use of or testing of friction reduction tools or shock tools, and any results that came from those.
We can't disclose any results from those. What we can say is that some, as the drilling engineers will tell you, some work and some don't. Some have negative effects on drilling in the BHA, but positive effects on ROP. So it really varies. We have been downhole with a bunch of those, and we're always happy to test these kinds of tools. We'll actually work with service companies and test their tools on actual customers' wells. We'll go out to Catoosa and test tools. So we kind of have that experience where we can help tool manufacturers determine if their tool is actually working the way they think it is downhole.
All right. So I know what's coming up next. I'll turn it back over to you, Dan.
All right.
Say bye to everybody.
Bye.
So let's get into that last question, or one of the questions we had there, and let's get into negative rotation or backwards rotation. What we have here is a plot of, again, bit RPM. So we are looking at bit RPM here versus time. Now, it's important to notice here, this particular example, we are reaming off bottom. So we've TD'd this section, we are reaming. We're not making the bit should not be making any contact with the borehole as far as actually on the face of the bit. So here's our zero line. I've kind of illustrated it, kind of highlighted it so you can see these 2 spikes. Well, let's analyze this a little bit. So what we looked at, based on what we've seen before, and if you're on earlier in the presentation, we can determine that this is our base motor output line. So with no surface rotation, this is where we expect our bit to be turning. Now, again, from our previous graphs and previous discussion, we can determine that these oscillations here are caused by the BHA or the drill string. Now, what we also notice here is that there's a lot of space between these oscillations, indicating that the BHA or the drill string is sticking. So if we take a look at this first very large example here, we have a long period of time where the string is absolutely stuck and we're getting very little RPM transfer, energy transfer to the bit. Now what happens is your string is stuck, you're still adding rotations at surface because we haven't stopped rotating here, or RPMs at surface are still constant. So you're adding rotations, you're winding up the string. Now eventually we're going to break that tension or break that force, that contact force between the BHA or drawstring and the wellbore, and we're going to have a release of that energy. Now, once we release that energy, we spin everything downhole. We're spinning the BHA, the entire BHA, your bit, your motor, your MWD, any stabilizers, any heavyweight. You're spinning that up to 500 RPM. Now, what happens is, the string isn't automatically going to stop. You're inadvertently you're winding up your string in the opposite direction now. So now you're winding up your string, and that energy also has to be released. So that inertial force forces us to turn to the left. Now, this isn't a constant. Obviously you can see we go negative 150 RPM. So 150 RPM to the left. Now this isn't a constant 150 RPM, so we're not constantly spinning to the left at 150 RPM, but it's a very, very quick event. But that's very alarming as well. I mean, think about all the mass that you have downhole. If this keeps happening, especially while you're reaming, when you think you're done with this section, you can twist off and you can leave your entire BHA or at least part of your BHA downhole. So this has very, very important ramifications. So string unwinds, you overcorrect. Now this is a very specific example. We're reaming, we're off bottom. Let's take a look at a more interesting example and something that I don't think many people have seen before. And it's also a negative rotation example. Here we have, what we have here is an RPM plot once again. We have two subs in the BHA. We have one at the bit, one higher up in the BHA, above the motor. Our orange line is our bit RPM, and our blue line is our BHA RPM. So if we take a look here, we see that the bit is in full stick. So we're seeing stick phases of the bit with very slight oscillations, likely caused by vibration, where the bit is trying to overcome that friction with the formation. But we're still seeing movement in the BHA. So obviously we wouldn't expect much movement. We wouldn't expect movement in this shape or RPM to become in this mode when this is happening. So what we decided to do is we put our engineering caps on and take a look at what's happening a little bit closer. But before I get into that, so this RPM measurements here are calculated using our accelerometers. And the way accelerometers typically work is they work on centripetal force. So no matter whether you're turning to the left or to the right, you're still going to see a positive rotation because it is in fact a rotation. So how do we address negative rotation? We use magnetometers. So for those of you who are not familiar with magnetometers, what they basically do is they measure the magnetic north. So I know this one's turning to the left. Let's assume that it was turning to the right. But what we see from magnetometers, we could also calculate our RPM from there. So when we take a look at magnetometers, one full sine wave indicates a whole rotation. So we can analyze our magnetometer signal and also determine RPM from that. But what this allows us to do as well is to determine if we have any negative rotations that aren't caught by our accelerometers. So when we take a look at that BHA RPM specifically by itself, and we take a look at the magnetometer signal, when we're having these strange kind of ramp downs after we see big spikes in RPM, we also notice that we have magnetometer reversals. Now, what does that mean? A magnetometer reversal means that before your tool can make a full rotation, there was an interruption and now you're rotating the opposite direction. So anytime we have mag reversals, and some of these are harder to point out, so I pointed out the more obvious ones. Anytime we have any of these mag reversals here, that indicates that we're turning to the left. Now, once it reverses again, we start turning to the right. We see positive rotation. Now, we can visualize this using very similar animation to before. So I'm going to stop this. This is a little different here. We're going to have two subs now. Our BHA sub is going to be shown with the green line circle. Our bit sub is going to be shown in the red line circle. So let's take a look at about a minute of what it looks like in real time to see that kind of negative rotation occur. So here we see the bit is in full stick or nearly full stick, and our green sub starts turning to the left. Now, once the energy is released and the bit sub is kind of catches on and starts rotating again, that rotation eventually catches up to the BHA sub. And this is happening multiple times. This is in real time. This animation is 1 minute of data. We're showing it over 1 actual minute. So again, energy release at the bit, energy eventually travels up to the BHA, and we start turning to the right again. So I will say this is a very isolated event. To date, this is the only time we've seen this. And the reason I decided to show it today is because it's interesting. It's something that we don't typically hear about, and we don't really know about that much. You know, some people will say that negative rotation is very prevalent, but what we found is it's not so. I mean, we might have, you know, very severe stick slip, very severe torsional oscillations, but negative rotation isn't as common as people would think. This particular example, what happened here is we had a very aggressive bit with a very strong high torque motor. Now what was happening is the motor was so powerful that when the bit took a bite that it cannot overcome, the motor turned the BHA above it to the left. So I'm gonna say that again because it's hard to follow. We had an aggressive bit. We had a very high powered motor. When the bit took a bite, the motor, rather than turning that torque into bit rotation, started rotating the BHA above it, and that led to negative rotation. Now, you might ask yourself, you know, we were definitely seeing this at surface. There's no way this wasn't caught at surface, and the truth is, it was not caught at surface. Same plot here, you know, bit RPM in the orange, BHA RPM in the blue, surface RPM in the black. So if we're looking at this strictly from surface, we say, yes, there is some stick slip occurring. So we know we need to address the stick slip. But what we don't know is that our BHA is spinning at 400 RPM and is also turning to the left. So that's why it's important to know that, sure, you may be able to correlate some events to surface, but there's never a concrete way to say we can definitely see what's happening downhole from surface, or we can definitely model what's happening downhole from surface. And I think that's an important distinction to make because a lot of efforts have been made to kind of make correlations, make models between surface and downhole. And while there is value to that, you do miss a lot of the picture, and you do miss certain cases. So you don't want to put yourself in a corner where you're saying definitely this is what's happening downhole. So David, I know this is a lot to unload, and I know this is a very interesting animation, very interesting topic. So I know there's probably going to be a bunch of questions on this. So go ahead.
So the first one was, and I know you answered this, but was it a motor BHA? And I'll let you cover that one again just to make sure if anybody missed it.
Yes, this was a mud motor BHA.
Let me scroll back here. Nicholas had one. Nick Brown over at Neuralis. Have you seen correlation between with the auto driller and input frequencies?
So we have ran some tests as far as kind of like torsional oscillation softwares and different programs at surface and kind of their viability. I know there's certain frequencies that they'll set for auto drillers and they're supposed to catch these things. We specifically have not been asked, and we have not tackled that specific kind of issue, mainly because that's something we're not given. So we try to focus on like, one, what are the issues? Two, what is the information we have at our disposal? So answer is no, but we definitely do have the ability to analyze that, and we have analyzed different auto driller, different stick slip mitigation surface tools, and their viability.
So here's another one. Oops, clicked on the wrong one. Sorry. So Dave Taylor, who's been very active in the comment section. So Dave, thank you for watching. I do appreciate it. Questions: can you analyze the effects when you use under reamers, roller reamers, or reamers in general?
So yeah, I mean, we obviously on the weight on bit transfer plot that we looked at before, we saw reamers hanging up.
Oops, leave that.
We saw reamers and stabilizers causing kind of a big disconnect in weight on bit. We can definitely take a look at other parameters to see, are we getting kind of dog legs in the hole? So yeah, we can definitely take a look at the effect of reamers, under reamers, things of that nature, provided that we have the correct BHA placement for our tools. So it's definitely something we do, something we've done. Different kind of hole opening tools or stabilization tools. We've done it. We continue to do it. We enjoy doing it.
Trying to see here. A lot of comments coming in, and everybody, thank you guys for participating. I know we did this one a little bit earlier. Do you guys have a differential pressure tracked? So
yes, we do. We get that data from the EDR. We can plot everything we're plotting right now with differential. It's always our data is always matched to the EDR. So anything that we display, we can definitely display with differential. So I'll actually get into that a little bit later on, and how one of the ways we deliver data to our customers, and we'll be able to see kind of everything in one picture, and it's very compact and concise.
All right, another one from Mr. Gupta. Can we quantify the chance/extent at which the string backs off? Great question.
So unfortunately we can't, because we don't know. I think the only way we could do that is if we had a torque measurement, maybe, but we're not measuring torque at the connections. I mean, one thing we could look at is if we start seeing some different vibrations or different frequencies of vibrations after we start getting these negative rotations. That'd be one way to look at it. But yeah, I mean, that's something we'd definitely be open to looking at. And to date, we haven't seen negative rotation with a string backing off. Not saying it didn't happen or it isn't happening, but we weren't in the right place at the right time to catch it.
So here's a question, and I'm guessing this is in reference to the last graph. Isn't it because of the distance between the two subs that there is an offset? I'm guessing the offset as far as the RPMs and rotation.
Yeah, so we do expect. So I'll go back over here. I don't know about offset exactly. So everything is time synced. So we know that these subs are seeing these in real time. We do expect an offset. I mean, the offset right here, let's say between the start of rotations here and the start of rotations here, is because of their placement. Now, if you're talking about the offset between the amount of rotation or the kind of amplitude, that's also again caused by the placement. We're at the bit, we're spinning with the motor as well, so we expect to see higher RPM versus the BHA. But we do kind of see that and take that into account. There is an offset between the two, and that signifies the transfer that happens between the bit and the motor, and the bit and the BHA.
So thank you, Mohammed, for that question. Here's one from Mr. Benning. How do these phenomena affect directional control, inclination, azimuth, or even micro doglegs? Is there any correlation on that?
So obviously directional control. I mean, so as far as surveys, let's talk about stick slip and built up torque. As far as surveys, if we still have built up torque when we're making a connection and that torque releases when we're off bottom, that'll also give you a bad survey. As far as directional control, I mean, this is while rotating. These events typically happen while rotating, so I wouldn't expect them to have a large effect on directional control in that sense. But as far as micro dog legs and kind of hole tortuosity, we do see that. We would expect more tortuous holes when we're seeing these kinds of events downhole because we're not using the bit in the way that it's intended to be used. And I'll actually, and we'll in the next section we'll get into a little more about how we quantify dog legs, tortuosity, and things that happen downhole.
So here's another one. How is stick slip data from the tool compared to what you get from MWD RSS data? What is the max stick slip measured? So first, it's important to determine what stick slip value you're using. To our knowledge, there are some people working on this, but to our knowledge, there's no set stick slip equation. Everyone uses their own. There's indexes, there's stick slip numbers, there's percentages. As far as correlating it to MWD, sometimes we'll see correlations, sometimes we won't. We're sampling at such high frequencies that we can see all these variations, whereas your MWD might see something like this, where we're seeing from the top drive, this black line, and say, oh, we're not really seeing stick slip. Or you might get, something on average here running along what your BHA should be seeing. So we will compare MWD data and our data, but it's important to realize that the way the sensors are configured and the way we're meant to capture data is very different. We try to be on the collar, measure everything that's happening to our BHA and everything that's happening to the bit, as opposed to an MWD, which you really want to isolate yourself from vibrations and isolate yourself from these kinds of events. So that gives you a hindrance as to what kind of data you can gather from MWD and what analytical value that has in drilling optimization and drilling dynamics. So the next question, I remember being a part of one of these projects, but I'll go ahead and let you guys. Would be interesting to see the actual efficiency of rig systems like Revit or soft torque in mitigation downhole. Has any testing been done with these?
Yes, we have. Yeah, so we've worked with some drilling contractors and they've tested their softwares, and it's easy to see. Now, it's important to address though that these softwares like soft torque and other ones that you'll see in the industry, they're specifically meant to address BHA and drill string stick slip. So it's always important to take that note especially when you're measuring it. Like if you're measuring at the bit, you don't see much of a change. Well, that's because you're not taking into consideration that you're spinning your motor when you're working with these softwares. So I would say that if we had a stick slip mitigation software, this likely wouldn't. We'd likely still see this happening because it is induced by a bit and motor problem. So the answer is yes. Yeah, we have done it before. We've quantified it to a percentage. We've actually given actual performance numbers, actual percentage numbers to customers who have asked us to analyze it.
So we've had a handful, because like now the questions are really rolling in. So thank you guys all for this. And one of the questions was in here, I believe was from one of the guys on YouTube. What tool can measure max? And this was like max RPM or essentially max stick slip. So the max RPM is a measure. I shouldn't be answering these. Sorry, Dan. Go ahead.
So the max RPM is a measurement, like you said. And to talk to kind of let's take a step back here a little bit. The stick slip mitigation softwares, that I want to be clear, are meant to address torsional oscillations, not necessarily stick slip. So I want to make sure that before there's industry guys that are super keen on this kind of go after me, those are torsional oscillation mitigating tools. But let's answer that RPM question. So the RPM is a measured value, obviously. What is the max RPM? I mean, our tool can measure up to, I believe, around 700 RPM, and we've seen 700 RPM. So we'll see bits, we'll see motors spinning way above the one you expect them to see. What's the second part? What's the tool can measure max?
Oh, sorry, I already skipped on to another one. Yeah, I would say you answered it. This one was asking, does backward whirl cause backward rotation or just anti-clockwise eccentric rotation of the BHA? Rotation
right,
of the BHA.
Right. So yeah, so backwards whirl does not cause backwards rotation. Like the second part of the question said, that's mostly a dynamic that occurs when you can still be turning to the right as you're supposed to. So that's a whirling dynamic as opposed to a torsional torsional dynamic. So they can be connected, and I would expect, or you would expect to see backwards whirl when you are spinning to the left in some cases, but they aren't always connected, and you can't say that you have one with the other in all cases.
Here's a quick one for Eric, who I know is watching in the background. Jot down that phone number. He's wanting to do a project with you guys. 432-214-4967. Sorry,
again,
Paul, for putting your number out there, but hey.
And again, hey, I'd like to encourage anyone that has questions to visit us at lodestarint.com. We have a contact us form there, and there you can also download our tool specs and different examples of projects we've done in the past, and just a little bit more about Lodestar in general.
All right. So the other thing is we've had a lot of questions about whirl.
Right.
Backwards whirl, forwards whirl, things of that nature. So I know that leads into the next segment. So I'll let you take it over, Dan.
Right. So let's talk about,
connect with us. Send us out. You know, if you guys are learning something and you like what you're seeing, please tag a friend in the comments or share this video, please. Sorry.
So let's take a look at whirl, and we'll get into whirl. But let's talk about what I'm calling the forgotten dynamic. So most people, when they talk about drilling dynamics, it's always, RPM. Are you seeing stick slip? Are you seeing, vibrations? Are you getting weight transfer? But one of the key things that people miss out on is bending. Bending has so much that we can learn from it, and it's a lot of times kind of forgotten. And so I really wanted to bring it up because to kind of bring awareness to it and make sure that people know that it's available and that it has a lot of different uses. So the plots here they're very, very interesting. So here we have a sub at the bit. We have sub at the bit. On the left-hand side, we have at bit sub with a 910 lobe air drilling motor with a roller cone bit. On the right-hand side, we have a 7/8 lobe mud motor with a PDC bit. So obviously what you notice here from the roller cone bit is that we have a kind of a triangle shaped pattern, obviously induced by the shape of the bit. Whereas on the right-hand side, we have more of a circular pattern. We can see a lobe configuration here, and it's very, very, it's not chaotic. It looks very clean. When we take a look at these over time, we can analyze changes in bit dynamics, changes in motor performance. When we start getting into more chaotic kind of bit whirl, so like answering the whirl question. So bending gives us a really interesting insight into what's happening at our bit and what's happening, between the motor and the bit. So before I move on to whirl again, I want to kind of, I know someone mentioned before, do you guys track diff? Do you guys have a diff track? I'll give you guys this example. This is an example of a WellCAD plot. WellCAD is a commercially available plotting software. We use it as a way to deliver data to our customers, and it allows us to plot everything all in one sheet, very concise. Obviously we plot these with time because that gives us the best granularity, but we can plot surface and downhole weight, surface and downhole RPM, differential here with our surface torque and our downhole torque, MSC. I know that was a question that someone asked about earlier. Vibrations, and we will plot our mud parameters. But if we take a look at vibration or bending rather, we did an interesting thing here. So what we're able to do with our tools, provided that we're in the correct placement, we're in the correct environment, we can actually measure and give qualitative values for wellbore tortuosity and micro doglegs, because we know they're happening and we know that our MWD is not catching them with surveys. We are able to, with bending, you get a true deflection measurement and you're able to analyze what's being missed from our MWD. So this particular example, what we did is we located an eye string 2,000 foot back from the bit. Then what we did is we said we matched the bit of slides that happened to the depth that our tool is located at. So I know it might be hard for you guys to see. I'll try to make it more clear when we release the PowerPoint. But in the black here, this black line that I'm following with my cursor, we actually see the MWD surveys. What does this say? No really bending. We're kind of pretty constant, likely staying around 1 to 2 degrees per 100 foot. When in reality, when we slide through these kind of areas with our tool, we're seeing very high bending, very large deflection. So what we're really missing from the MWD, we can capture with our tools, capture with bending. And it's something that people have talked about doing, but we're not really seeing a lot of being done in the industry. So that's one really key thing that we can do, and we like to show. And we can do this, and we've done this, and we continue to do this. But looking at reamers, you know, if you guys are using some kind of tool to open the hole or to make a more concentric hole, we'll place tools above and below those to see what kind of changes in dynamics we see, and things like that. So I mean, bending is very, very useful. It's just being very underutilized. So and this here is very eye-opening when you take a look at when you show this to engineers, because you might say, hey, why am I having trouble getting casing to bottom? I only have a 1 degree dogleg or 2 degree dogleg, when in reality, you know, you have these really high bending areas where you might be creating a micro dogleg that you're essentially missing with your MWD. So going back to whirl, what we can do with bending, we can see the path that we're taking with the BHA, and we can see when we can identify stable versus chaotic drilling parameters. So obviously there's a big shift here. We know that there was something that happened or an input that changed, that caused this change. If we analyze the shape and the prevalent directions of the bending, we can determine if there is something in the BHA or if the drill string is kind of leaning toward a certain direction. Then we can analyze that and see if it's affecting our performance. And then also determine the impact of downhole tools on whirling. Are you adding a tool that's creating more whirling downhole when it's trying to address another issue? So let's kind of finish it off here with this animation. And what we'll see here is we'll see different modes of whirling, and we'll kind of answer some questions here. So what we're looking at here is we're plotting bending. We're looking at our weight on bit here in this track, and we're looking at our RPM on this track. So obviously we see a small cluster of data points. That means we're very stable. We're staying very constant. We're not really moving around too much. Now, once we start seeing some changes in weight on bit, we'll start to notice some particular patterns that come about. So we apply some weight. We start seeing more whirling, like the forward whirl that we're seeing. And we'll see it vary with weight. So you obviously very different. We're able to measure the kind of amount of whirl. It's like how far are you deflecting? How much are you deflecting? That's very important. So not just say you're whirling, but also say you're whirling this much. Then we get into a very peculiar position where we see more of a triangular kind of pattern, you know, likely indicating 3 points of contact that you're getting in the wellbore. And again, a very specific triangular pattern that we're getting in bending. And we'll see this shift over and over again, and it just kind of continues changing, and it continues occurring. So again, you know, this is something that I believe, and I think some others may believe in the industry as well, that it's very underutilized because there's a lot of value to it. And it's interesting. I mean, look at this. I mean, where else would you see this? I mean, you're definitely not catching this kind of things at surface. So with that, that's my last animation. I'll play it again from the beginning. I'll let this play, or I'll rewind it a little bit so you guys can take a look at it again. But I think we can let this play and see what kind of questions we have.
Let it keep playing, Dan. Let it keep playing. I love this animation. All right, so we've got a couple of really good questions that have come in here. Guys, thank you guys so much for watching. I would love to be able to hear in the comment section if you guys have seen stuff like this before, or I should say, if you've never seen anything like this before, if you've never seen animations like this before, please let us know in the comment section, right? That's where, you know, we really want to be able to get your feedback, because I want to make sure that I'm bringing you guys the best that we can on the Vidor Locksmith Show. So, you know, y'all's feedback is absolutely paramount. Hi, sweetie. Yeah, you can sit in that chair. That's fine. All right. So first question, this one comes in from YouTube. Is the bending moment measurement azimuthal?
Azimuthal. I need to break down. I need more explanation of that. So we do have directions. So
well, I mean, we have the XY coordinates in the
we have XY coordinates. So it is directional. So we can say when it's bending in this direction, you know, the magnitude is this. So we can plot it. That's how we plot the kind of like the two plots we're seeing whirling in different modes of whirling. So azimuthal, I would say, yeah, I mean, it's directional, right?
So then the next question from Jackie G. So another question about the measurement, and this is a very good question. Is the bending calculation performed by using your accelerometer to calculate distance displacement, as you mentioned earlier?
No. Our bending measurement is a force measurement strictly. So when we're plotting this, when we're showing this, we're not showing displacement. We're not saying your tool is, you know, moving this much away from the center of rotation. We're saying this is the force that your BHA is seeing. So we can make some inferences. You know, we can do some calculations, determine if we have the Young's modulus, and we make kind of a model. We can determine, you know, how much deflection is this in real life when we're measuring this kind of bending. So it is possible. We can't do it, but we do not. Our bending is specifically a measured value.
All right, so I want to run through a couple of these responses real quick, because this makes me really happy to be able to share this with the industry. And I know on behalf of Lodestar, I know all the guys at Lodestar are really happy to be able to do this, you know, my alumni group there. So never seen animations like this from Dave Taylor. First time seeing an animation of whirling. Tells a different story of what's going on. Great animation. Lee House, thank you. Great animation, great data, Travis. Never seen this before. Thanks for the lecture. I don't know who the LinkedIn user was on this one. Sorry. Sometimes it just doesn't show y'all guys' names. I don't know why it does this. Seen static plots, but animations like this, great visualize to see what's going on. Great animations for sure. First time seeing this. Right, guys? So this is the whole point of this, is that we want to be able to share with you guys stuff that you may have never seen before, may never have been able to conceptualize before, and gives you that opportunity to be able to look at something in a whole new light. And that's why I thought this would be such a great presentation. And I wish everybody in the industry could just take 5 minutes to be able to go through and watch all of these animations to be able to have a better understanding of what's happening with their BHAs. So let's see what we could do with some of the questions. So this is a good question, and this may be something you guys have been working on since I haven't been there. Can the tool record caliper hole size data?
No, we don't have a caliper, a way to record caliper. I mean, there's ways that we can attempt to record caliper. So I'm not saying it's not possible, but you know, we'd definitely be open to discussions with anyone who would be willing to, you know, go into detail about ways we can do that. Excuse me.
Yeah, guys. So if you have any more questions, be sure to throw them out there. We'd love to be able to get any of them answered. I'm trying to scroll back through here to be able to see if we've got any. So Sahet, who's been very active in the comment section, very thankful for having him watching. Have you able to visualize whirling path with accelerometer data only?
Yes. So that's kind of the usual way it's done. So it's not uncommon to do that. So yeah, we can definitely visualize whirling with acceleration data. And the reason, and you guys might have noticed, I kind of skirted away from acceleration data so much for this presentation. The reason being is that I like to highlight that there's such, we need to place more importance on actually having strain gauges and weight and torque and bending downhole, because when you have only acceleration, you're missing a large part of the picture. You're getting 50% of the picture or less with just acceleration. So it's very important to always try to gather as much data as possible downhole. And acceleration I can do a whole presentation of an hour just on acceleration on its own, and David can attest to this. And we have so many great examples. But yeah, to answer the question, yes, we have, and yes, we can.
So a comment from Lee House, something like this could make some explanations at site much easier when trying to change parameters while getting resistance from the operator.
We agree, and we that's why we're working on real time. That's why we're deploying real time tools, because we want people to see this, and we want people to realize that, you know, you may think that everything is going fine downhole, but in reality, you're tearing up your BHA, you're tearing up your bit. So I do agree, and we with the advent of real time and what we'll have here soon, I think we're going to be able to really help our people in the field, and also help people in the office as well, because sometimes we'll have it goes both ways. You know, sometimes operators will want to tell something to their directional or rig hands, and it doesn't always go as planned because they can't really prove it. So here, what we want to give people is the tools to prove what they think is happening, and also show them what they don't know is happening.
I do want to put this out there. Fred Harvey's been watching. Fred, thank you so much for watching. We've worked with him in the past, or Lodestar has worked with him in the past. I gotta get that wee thing out. What's funny is like Dan and the Lodestar team are actually just like 20 minutes down the road.
Yeah.
And so we could have done this in person, but hey, we're doing it over the internet. We got a comment from Drew Wood, who's the most infamous guy on LinkedIn about talking about real-time mitigation for protecting MWD tools. So Dan, if you want to comment on real-time mitigation and what you guys would be able to do with being able to have the real-time stuff here in the near future.
Right. So real-time. So to mitigate these issues real-time, we would, one, know that it's happening downhole, and then two, have plans and talk with the engineers, drilling engineers, talk with people at the rig and let them know what to look out for. We'll have flags in place to let them know, hey, you're experiencing stick slip, change these parameters. And obviously, rather than the historical approach of using only recorded data, we'll be able to say, change this parameter, and then look for the response. So there's our real-time mitigation right there. That's how we move into that realm.
I just want to say we got never seen downhole animation on weight on bit and RPM. This is from Kennedy. I did see his stuff. Kennedy's one of the guys that's very active on LinkedIn, being able to help promote the show. And I appreciate that very much, sir. So thank you for that. Ozzy Silva, great presentation, gents. One of the guys that's out there who's in this realm, who's super smart in this area as well, James Nito, who's got a consulting business looking at data like this. So him plus Lodestar, a great combination, great presentation, guys. You need decent telemetry. I'm sorry, I clicked on the wrong one there. Water pipe. Nope, that's a. Thank you for the presentation from Hit. Thank you. There was a question in here. Here we go. Sorry, everybody's commenting so fast. I got to find them. Have you correlated your recorded data with simulated vibration data that was theoretical? I think. Are you on mute?
About that? Yeah, we have.
You weren't on mute. You're just unplugged.
Yeah. So actually, I'm making sure I do not have my laptop dying, you guys, right now. So. There we go. Yeah. Everyone's still there?
Yeah, we're still here. Keep going, man.
Apologize for that. So we have, yes, we've worked with customers who've created models from our data, and then what they have done is they've simulated events downhole and then ran those parameters to either confirm or deny whether that's actually happening. So yeah, we do that all the time. We have customers reach out to us who want to do modeling, and that's obviously one of the next steps in kind of using this data is, fine-tuning models continuing to fine tune models, but also reusing the data because you never know what's going to happen. It's always important to have something downhole because the one time you do not have a tool on hole is when you're going to fail a bit, or you're going to fail a motor, or you're going to have a twist off, and you're really going to regret that you didn't capture that.
So we've actually had this question come in a couple of times, people asking about the Lodestar tool being used in conjunction with Tomax. I know what the answer is, but I'll let you do the work here, Dan.
So obviously we can't disclose performance of third-party tools when we're downhole. We try to keep that to our customers. Obviously, it's part of the confidentiality that we try to keep with our customers. We have been downhole with Tomax. I'll stop it there. I don't want to say anything positive or negative, but you know, we do work with a variety of different tool manufacturers. We've seen everything and anything that people put downhole, every kind of jewelry. So we've seen what happens. We know what works. We know what doesn't, and we know what's causing more issues than they're supposed to.
So here's one from Naveen. This is interesting. What is your take on using these to move forward towards closed loop automation for drilling?
That's the ideal situation. That's where we want to move. You know, we want to move towards automation. That's obviously one of the big steps and one of the big hurdles in the drilling industry, and that I feel like we're behind on in technology wise. So once we get, obviously the next step for us is real time, which is kind of a big hurdle that we're handling towards automation. So definitely closed loop rig automation is the goal. And if we can use our data and use actual downhole sensors that are calibrated to known standards, that are giving you real measurements to make those decisions, and you know, we'd love to be part of it. So we're definitely hoping to venture into that once our real time is released next month.
So this is from Mr. Khan, Khan. I can do that part. What frequencies are you guys observing data at?
So we measure data. We record and sample together at 20, 50, and 100 hertz. Now, if it means what frequencies we're measuring from, you know, reactions downhole, then that depends on the drilling conditions and what kind of tools happen. But our tool records and samples at 20, 50, and 100 hertz. Currently, I'll say currently.
Are there plans to include sensors or high frequency sampling to detect high frequency torsional oscillation? Ray Lamborn from over at Baker Hughes. Ray, thank you for always watching. I'll send you a text after the show because we want to get some Gibson reports in y'all's hands. So
yes, we do have plans to move to higher frequencies to catch these HFTO, which has kind of become a hot topic in the industry. So pretty soon we will have the ability to measure in the kilohertz to kind of capture those and other dynamics, which you know, if we think that moving from 1 second to 20 hertz was a big leap, moving from 100 hertz to a kilohertz is going to blow people's minds.
It's like taking it from a water or a fire hose.
Exactly.
Have you correlated your tool output with the MWD output, and do they match?
So I'm going to assume here you're talking about the dynamics that we measure from the MWD. And yes, they do match, but not as great as we'd like them to. There's a lot of dynamics that are missed by MWD, obviously because of the placement and the way that MWD is designed, which is to mitigate and not see the vibrations that you might see from a collar-based tool. Now, if you're talking about the MWD output from the RPM kind of pulses, no, because we don't know how to decode those.
Here's a great question. I'm really interested in hearing this one. Special considerations with using non-conventional bits, like the Chimera bit, which is a PDC plus roller cone hybrid.
We have been downhole with kind of those combo type bits that have PDC and roller cone components. Special considerations, I mean, you know that there's going to be different dynamics. Obviously can't disclose what exactly those dynamics are, but you do expect different dynamics. We have been downhole with them, and it's very interesting to see them work.
Which is funny because, like, I know everybody's like, so tell me everything you're not allowed to say.
It's like, tell me about this tool and that. So it's like,
I can speak to this, having been part of the organization. There are many times in many meetings where people are like, well, what about this? And you're like, that's a good question.
It's a good
just
question.
can't, you have to keep that, what somebody pays for is their information. So
yeah, we make sure that's key for us. We're not disclosing, we're not using data to optimize someone else's parameter. We're not going to tell you what your competitor is doing across the street from you. So we do take pride in trying to keep that confidentiality with our customers and making sure that we're disclosing information that can be disclosed.
So somebody asked a question as far as, but somebody else also answered it for you. The tool actually oversample at 20 and 50, 100 hertz. The rate is already anti-alias rate. So somebody was asking if your sampling was aliasing, but no. This is awesome. You guys are answering the questions for you.
Thank you.
Yeah. Thank you guys for tuning in on YouTube and on LinkedIn. So how do you confirm the calculation is correct?
So calculation. So I'll give one example of I'll go into one sensors. So we do have redundancy in our sensors. So this allows us to get different calculations for RPM and pick or determine which one is the best estimation. So we use accelerometer RPM, we calculate magnetometer RPM. So we already have two sources of RPM data. All our sensors are calibrated up to 150C. So we know that everything is good there. We have certs. We put these in load cells. We've confirmed that they're reading correct. And then, we do due diligence. We take the time to make sure that we're providing customers with a quality product, because, we're selling data. We're not necessarily selling you a motor. We're not selling you another bit. This is our only form of business. So we're not going to show you data in hopes that you run our stabilizer.
So I just have to put this up there.
Tongi. All right. Great.
Tongi. So Tongi's part of the organization. He's like the mad scientist behind a lot of this. He's been with the from the origin of this tool. So if you guys have any like super technical questions, feel free to throw it at that human calculator.
Right. Tongi had a key in designing the tool. This is his baby. He's been with the tool for the longest time. So any questions about sensors and how we do things, it's definitely worth asking Tongi. But obviously reach out to us and we can set up a conversation.
I was joking around before the show, Tongi, that your French accent would come through in the comments, but obviously it didn't. So feel bad there. Here's one from Dave Taylor. Can this be used with foamed and/or managed pressure drilling applications?
Yes. Obviously we drilled in air before. Obviously we drill with mud all the time. So air, foam, what have you. That's very similar. Managed pressure drilling, also very similar. So yeah, we can. We take into account all temperature and pressure when we're processing the data. So no, there'd be no issue using this in an MPD or a kind of different fluid application other than mud.
So to answer one of the questions earlier, Lee House said tight hole. That's right. So this one is from Scott McNeil. Scott, sorry, your picture doesn't show up, but presumably your tool picks up axial vibration. If so, how often have you seen it?
Every single time. Every single run is going to have axial vibration. Now, it's important to distinguish axial vibration from actual bouncing. If you have axial vibration at the bit, it doesn't necessarily mean that you're coming off bottom and you're actually slamming your bit back on the formation. But yeah, axial vibration is pretty prevalent everywhere in the drill string, and we do see it quite often.
Here we go. How about when you drill with magnetic interference, is it affected?
The only sensor that it will affect would be our magnetometer. But even so, it's not always the case. It's really just, did they rub the motor on the side of the casing when they're going down hole? Now our mag sensor is saturated. So magnetic interference won't have an effect on our accelerometers. So we won't have an effect with RPM, vibration, weight, torque, bending. So it doesn't affect our readings from our tool.
So here's another great loaded question. We'll see what Dan has to say to this. I would assume that if you have sampled situations with smaller and larger drill pipe diameters, you might be able to recommend ideal drill pipe diameters.
I would be able to recommend them, yes. And a lot of customers are actively trying to answer that question. And we try to. It's important when we're looking at this is that, when we present to customers, we don't want them to do one run. Like, you don't do one run, and that's not the golden ticket to solving all your drilling problems. What we really want to do is we want to set up a testing program that allows you to change one component at a time, so you can capture changes as they happen, as opposed to you change your bit, you change your motor, you change your stabilizer placement, and all of a sudden the dynamics change, but you don't know what it's caused. So to answer your question, yes, we can recommend ideal drill pipe diameters, but it's going to be very specific to your application. Hole size, what is it? Your vertical? Is it your lateral? Is it your curve? Things like that.
So this is actually from an NOV employee, Mr. Khan. Says, "Great answer, guys. Dan is very knowledgeable." Yes,
thanks.
He is.
I do try.
I agree. All right, guys. The questions are slowing a little bit here, so if I see one more, we'll go ahead and throw it up on the screen. As for that, I'm going to say, guys, here's what I need y'all to do. First of all, send in a LinkedIn connection request to Dan. Just flood his connection inbox. Get connected with the guy. Also, if you guys, Eric Drury is also part of the Lodestar team. There's a couple of other guys. Follow their LinkedIn page. Go ahead and check out their website for more information. We will be putting this presentation out, the PowerPoint presentation, once Dan gets it over to me in a little bit more condensed format. We'll put it out hopefully on Monday. That's also when I'll send out the email if anybody has subscribed to the show email calendar. Next week, we've got Calvin Holt coming on to be, I think the topic is questions you should have asked your parents about managed pressure drilling. And the week following, on Thursday, remember this can be on Thursday, July 2nd, since July 3rd is supposed to be a U.S. holiday or observance of a U.S. holiday. On Thursday, 10 a.m., July 2nd, I'm going to have David Ransomwood, who's going to come in and talk about financials for non-financial people. The following week, we're going to have Pete Aird. Later in the schedule, I've already lined up Mark Anderson. Mark Anderson's going to come on and talk about the digitization of the industry. Kurt Meyer is going to come in and talk about prospecting, how to be able to do risk analysis, reservoir engineering, those kinds of things. He's a great guy who's put on some amazing content on his YouTube channel. So be sure to check him out here in advance. Everybody's coming in and definitely bringing in the comments now. We do appreciate it. Guys, if you haven't connected with me, go ahead and connect so that way we can stay connected and you guys can see more of like the shows and stuff. Also, we're now broadcasting live on both YouTube and LinkedIn. I know there were some issues here today as far as the LinkedIn stuff. Some people were saying that it was kind of blurry, but then I got a message from somebody saying it was a little bit clearer on YouTube. It's completely up to you guys where you watch from, but you can always go back and watch these episodes. And in any of the past episodes, last week was Steve Noss, where we talked about what is managed pressure drilling. It was one of the top rated shows that we've ever had. We didn't break any records today, Dan. No big deal, but we still had an amazing show. So we do have a handful more questions that have just come in. So we'll throw this one up there. Mr. Shen, when you place a sub between the bit and the motor, do you have concerns on broken motor shaft? Any ways to mitigate?
Yeah, I mean, there's always concerns of that happening. In my time, I've seen it once. You've seen it once, and then that was because we had some really serious dynamics happening. Mitigating it, I mean, that falls on making sure that you're provided a quality motor, because we haven't, like I said, we haven't seen it much, and we've been through the ringer at the bit, between the bit and the motor. We've seen pretty heavy dynamics, but yeah, I mean, there's not really a concern. I wouldn't say there's a concern there. The only issue would be if you know that's happened in the past, then that might be a red flag to running us there.
So Drew says, great question. Let's send this PowerPoint to every company man that we know.
Go ahead. I'll let you talk.
I'll leave that up to you guys. On Monday when this thing comes out, you guys can just make a email blast that goes to every company man out there. So that is completely on you guys. Armin says, "Hook 'em."
That's right. Let's go.
So this one's from. Oh, I hate it when I do this. Tafik. The tool measures shocks. It would be interesting to see shocks while drilling stage tools or shoe track.
Right. So,
yes, it would be.
It would be interesting, yeah. But the way our sensors, the type of sensors we have, we measure vibration. So we don't measure shocks currently. But we do see that the kinds of vibrations and the kinds of dynamics that happen when we're drilling shoe tracks or stage tools or anything of that matter.
And here's the other twin for everybody that wants to. Why is my camera going bad? Hold on, get this thing down there. Can you say hi to everybody? Oh, you're going to be the shy one. Of course you are. All right, guys. Thank you guys all so much for watching. We really do appreciate it. Thanks, David and Dan. Fantastic presentation. Thanks, Mr. Gupta. I do appreciate it. All you guys out there that are watching, we really do appreciate the support. This show is essentially for everybody out there in the industry that just wants to learn more and be able to do more. You want to get down, bud? Oh, don't stick on that. This show is all for you guys. I just ask that you guys share, like, comment, let other people know about it so they can get free information sessions. Nobody's having to pay $15 for this webinar or anything. We're doing this 100% for free. You can watch everything here on LinkedIn and on YouTube. We'll have the show minutes coming up, like I said, on Monday. And if you guys haven't signed up yet, please sign up for the email list. I'll be sending that out, I think, on Mondays and Thursdays with information on upcoming shows and on past shows. And if you guys have any requests, if you want to be on the show and you can do an educational presentation, get in touch with me. Let's do it. If you have somebody you would like to nominate to be on the show, get in touch with me. Let me know about it. If I've missed anything, if there's things that you guys would like to be able to see us cover, get in touch with me. Let me know. We're here to be able to serve you guys. This is just something I do for fun. It's been a great time. Dan, thank you so much for coming on the show. You are a true friend, sir. Eric, thanks for allowing Dan to be able to come on the show. I think you're there in the background if you want to stick your head in. You guys have a wonderful Friday. And as always, guys, know your industry.
All right, thanks, David.
No worries. Where's the button? Nope. I didn't have this pulled up in time. Sorry, guys. There we go.